Fermat's little theorem. It states that if P is a prime, then any integer A satisfies the relation A raised to P congruent to A modulo P, and any integer A not divisible by P satisfies the relation A raised to P minus 1 congruent to 1 modulo P. Let us consider the first case, when P does not divide A, that is when the GCD of A and P is equal to 1. First we claim that the set 0A, 1A, 2A, etc. P minus 1 into A is a complete set of residues modulo P. Here note that the set 0, 1, 2, etc. P minus 1 is a complete set of residues. In fact, this is the set of least residues modulo P. We have formed the new set by multiplying each element of this set by A. And we claim that the new set formed is also a complete set of residues modulo P. To prove that this set is a complete set of residues, we need to show that no two elements of this set belong to the same residue class. That is, we have to show that if 1A belongs to one residue class, then another element, say 2A, will belong to some other residue class, and so on. So we need to show that no two elements of this set belong to the same residue class modulo P. In order to prove this, we will be assuming that some elements of the set, say IA and JA, belong to the same residue class. If these two elements belong to the same residue class, then those two will be congruent modulo P. That is, IA will be congruent to JA modulo P. But this relation would imply that the difference IA minus JA will be a multiple of P. That is, P divides I minus J into A. But we know that P and A are relatively prime to each other. That is, we have already assumed that P does not divide A. Hence, if P divides this product, this would imply that P must divide I minus J. But we know that I and J are members of the set 0, 1, 2, etc. P minus 1. That is, by our assumption, I and J are both less than P. So the difference will also be less than P. So this relation can happen only if I minus J is equal to 0. So I must be equal to J and IA must be equal to JA. Thus we can conclude that the set 0A, 1A, etc. P minus 1 into A is also a complete set of residue, and hence we have two complete sets of residues here, and we can observe that 0 is congruent to 0 into A, and we can see that every element of first set will be congruent to a unique element of the second set. So we can say that 1A, 2A, etc. P minus 1A is simply a rearrangement of the elements 1, 2, etc. P minus 1 when considered modulo P, since each of these elements will be congruent to exactly one element from this set. So we can consider this as a rearrangement of these elements. Thus, it follows that the product of numbers in the first sequence, that is the product 1a, 2a, etc. p minus 1a is congruent modulo p to the product of numbers in the second sequence. The product of numbers is 1 into 2 into etc. p minus 1. Hence we have the relation 1a, 2a, etc. p minus 1a congruent to 1 into 2 into etc. p minus 1 modulo p. And we can see that the product on the left side consists of p minus 1 copies of a into etc. a p minus 1 times. So this product can be expressed as a raised to p minus 1 into the remaining factors are 1 into 2 into 3 into etc. p minus 1, which can be expressed as p minus 1 factorial. So the left hand side will be a raised to p minus 1 into p minus 1 factorial, and the right hand side is 1 into 2 into etc. p minus 1, which is p minus 1 factorial itself. So we can express the relation as a raised to p minus 1 into p minus 1 factorial congruent to p minus 1 factorial modulo p, which implies that p minus 1 factorial into a raised to p minus 1 minus 1. By taking p minus 1 factorial common to both terms, we get this product is congruent to 0 modulo p. That is, the product p minus 1 factorial into a raised to p minus 1 minus 1 is a multiple of p, which implies that p divides the product p minus 1 factorial into a raised to p minus 1 minus 1, which would imply that p divides a raised to p minus 1 minus 1. That is, p divides the second factor, since p minus 1 factorial is the product 1 into 2 into etc. p minus 1, and we know that each number involved in this product, say 1, 2, etc. p minus 1, are all relatively prime to p. Hence, p minus 1 factorial will be relatively prime to p. That is, GCD of p and p minus 1 factorial will be equal to 1. Hence, p divides this product must imply that p divides the second factor, a raised to p minus 1 minus 1. This relation can also be expressed as a raised to p minus 1 congruent to 1 modulo p as required. Thus, we have shown that if p does not divide a, then a raised to p minus 1 is congruent to 1 modulo p. We can multiply both sides of this relation by a, that is a raised to p minus 1 into a, that is a raised to p, and 1 into a is a. So we get the new relation a raised to p congruent to a modulo p, even if p does not divide a. Here we have applied the relation a congruent to b modulo m will always imply that AC congruent to BC modulo m. Next, let us consider case 2, that is when A is divisible by P. Then the difference a raised to p minus a can be expressed as a into a raised to p minus 1 minus 1, and it is obvious that this product is a multiple of a, that is a divides a raised to p minus a. But we know that p divides a in this case. So p divides a and a divides a raised to p minus a. So by the transitivity of divisibility relation, we must have p divides a raised to p minus a. That is, a raised to p is congruent to a modulo p. Thus, if p divides a, then a raised to p is congruent to a modulo p. Thus, we have proved that if p does not divide a, then a raised to p minus 1 is congruent to 1 modulo p, and for any integer a, that is, in both cases we have shown that a raised to p is congruent to A modulo P.